This video is part 2 of section 4.2, Integral Exponents. In part 1, we used the exponent laws to help simplify expressions with integral exponents. We'll still be using the exponent laws in part 2, but we're going to be looking at converting a power with a negative exponent to a power with a positive exponent and applying the exponent laws to solve a little bit harder examples. Powers are often the most simplified when they have positive exponents only. There's a principle or rule that we use to make any negative exponents positive. That principle is a to the power of negative n is equal to 1 over a to the power of positive m. When you have a negative exponent with a base, you can bring the whole power to the opposite side of a fraction. So in this case, it was on the top, so now we're going to move it to the bottom. And any positive exponents are going to stay where they were. In this case, there weren't any, so we leave a 1 on top of the fraction. The exception to this rule, well, as long as a does not equal 0, then this rule will work. Similarly, if you have a negative exponent already on the bottom of a fraction, so like say a to the power of negative n, that can be equal to a to the power of positive n. So again, wherever the negative exponent is, the whole power is going to move to the other part of the fraction. So now it moves to the top. And the 1 is just like, it's like saying 1 times a to the power of n, so it's just a to the power of n. And a cannot equal 0, because you cannot divide by 0. Example 1, we're going to look at 2 to the power of negative 3. We want to write an equivalent expression that has positive exponents only. We see a negative exponent with a base of 2, so we're going to apply the first principle that we wrote above, where the 2 as a base goes to the bottom of the fraction and its exponent becomes positive. And we leave a 1 on top of the fraction. And that would be our simplified answer. Our second example is 1 over 3 to the power of negative 2. This time our negative exponent is on the bottom of the fraction, so it's going to move to the top and become positive. So our simplified answer is 3 squared. Alright, let's look at 4 more examples that have a little bit more going on in them. The first example here is 5a to the power of negative 3. And we want to write these expressions using positive exponents only so that they're more simplified. For example 1, 5 has an exponent of positive 1 and a has an exponent of negative 3. Only negative exponents move. Any powers that have positive exponents are going to stay put where they're at. The 5, because it has a positive exponent, is going to stay on top of the fraction. And the a to the power of negative 3 will move to the bottom and become positive. The second example is negative 4 over a to the power of negative 3. The negative 4 is a negative number in itself, but we have to look at its exponent. We don't worry if the actual base is negative. The exponent of negative 4 is going to be still a positive 1 because there was no number written there. Because negative 4 has a positive exponent, it's going to stay on the top of the fraction. A to the negative 3 is going to move to the top and become a to the power of positive 3. Notice how these two expressions are multiplied together. We are dealing only with multiplication and division of powers. We have no addition or subtraction for these rules. Example 3 is 2x to the 4, y to the negative 2. Identify your exponents. 2 has a power of 1, x has a power of positive 4, and y has a power of negative 2. The positive exponents will stay where they are at in the fraction. So x to the 4 and 2 will stay. Y to the power of negative 2 will move to the bottom and become y squared. And that is our simplified answer for that one. Lastly, for example 4, we have to work a couple exponent laws first to simplify, and then we'll switch the negative exponents to positive exponents. Let's look just inside the square brackets first. We have a negative 4 outside of the very insidemost brackets. X and y are different bases, so we can't add their exponents. So then we look to the negative 4 exponent to bring it into the brackets. To do that, it gets multiplied into every exponent in the brackets, times them together, and we'll leave the square brackets for a minute. We will get x to the power of 2 times negative 4, which is negative 8, and y to the power of 3 times negative 4, which is negative 12. And that is still an expression raised to the power of negative 2. The next step is to bring the negative 2 into the brackets, and it's still the same rule where you bring the negative 2 by multiplying it in to any exponents in the brackets. So times them. And we will get x to the power of negative 8 times negative 2, which is positive 16, and y to the power of negative 12 times negative 2, which is positive 24. Because our final answer ends up having positive exponents only in it already, then that is the simplified answer. Last, let's quick look at an example where we simplify and then evaluate. So if we have 8 over 8 to the power of 3, and that's all raised to the power of negative 4, what can we do here? Well, I like to start inside the brackets and work my way out. So if there's anything I can simplify inside the brackets, I want to try to do that first. Then I'll deal with the negative 4 on the outside. I can subtract those exponents because they're powers with the same base. So this is 8 to the power of 1, and divided by 8 to the power of 3. So we're going to get 8 to the power of 1 minus 3 inside the brackets, and it's still to the power of negative 4 outside. Well, 8 to the power of 1 minus 3 is negative 2 to the power of negative 4. And finally, this is a power to a power, so we're going to multiply our exponents together, and you get 8 to the power of, well, negative 2 times negative 4 is positive 8. If you actually calculate 8 to the power of 8, you would get a very large number. It's going to be 16,777,216. Now, this is your simplified answer. 8 to the power of 8. This big number is your evaluated answer. So if it says to simplify, then evaluate, those are the things you want to do. The simplified answer still has exponents, but you cannot apply any more exponent laws. And lastly, evaluating is to get an actual number without an exponent as your answer. Now let's look at a typical word problem that you might see that involves exponents. There are lots of examples in real life that involve exponents, and population growth is one of them. In this question, we're looking at the growth of a population of bacteria that is represented by the equation n equals 1500 times 3 to the power of t, where n is the estimated number of bacteria and t is the time in days from today. How many bacteria are there after 5 days? And how many bacteria were there 3 days ago? So to first solve the first part of this question, we want to see about how many bacteria there are in 5 days. So we start with our equation, and t is the time in days. So 5 days from now is positive 5 for t. To solve this, we need to use order of operations, and exponents are solved before multiplication. 1500 will still be multiplied by 3 to the power of 5, which is equal to 243. Now we can multiply 243 and 1500 together, and we get 364,500 bacteria. For part B, we're looking at 3 days ago, how many bacteria were there. Let's start with our equation again. This time, we're looking at 3 days ago from today. So for t, that's minus 3 days. So we sub negative 3 in for the exponent. Now we can solve this, and 3 to the power of negative 3 is equal to 0.037 ... We want to use our unrounded number and multiply that by 1500, and we get 55.5 repeated, so 55.6, or approximately 56 bacteria were present 3 days ago. This is a good example of a word problem where you have to use positive and negative exponents. Negative exponents, you'll often have to count backwards in time, number of days or years or something like that. I hope this tutorial video has been helpful for you, and thanks for watching.